Okay, in chapter 6, we're going to talk about analytic geometry. The part of analytic geometry we're going to be talking about is called conic sections. And before we actually look at conic sections, we're going to take a look at something historical. What we'll see in this video, what we're going to watch, is that a lot of the work that we do almost entirely is due to this man, Apollonius of Perga. Now, Perga is an ancient city in Turkey. So he was actually born, I believe, in Turkey, Perga, and he died in Egypt. The timeline is about 150 BC. So, contribution of Apollonius, tremendous contribution to the field of analytic geometry. Apollonius has 8 books on conic sections. The first 4 books take on the topics that we look at today, of course, in much greater detail. And the latter 4 books simply treat the topics in more depth. The books of Apollonius have all been translated into other languages. So, for instance, down here, I have copied a page from the Arabic translation of a couple of pages of his book. So rather ancient work that has stayed with us even until today, and it's amazing that something that was done over 2,000 years ago still being used today. So just want to give you a little historic background into the work that we're going to be doing today, so maybe we appreciate it a little bit more. So let's begin with talking about conic sections. Now, why are these called conic sections? Conic sections, that's when we look at the points of intersection of a double-napped cone with this flat surface. Now, the cone itself is generated by a generator. So, for instance, this would be my generator. And if you look at the center, which is a line, that's what it is. So think about a ruler, for instance. This is a ruler that's about a yard. Whatever, the length doesn't matter. So that's my ruler. That's the center of the ruler. Now, if I rotate this generator, that's what we call it, the generator, about this, the vertical axis, about this is the axis that we're going to rotate it. So we're going to revolve it in this direction. And again, it doesn't matter. You can revolve it in the other direction. Now, as the top rotates in this direction, the bottom will revolve in this direction, correct? As well. Both, in other words, the top and the bottom, they can revolve in a clockwise or a counterclockwise direction. It doesn't matter. As a result of this rotation around the axis, then we're going to get what we call a double-napped cone here, okay? So let me write that for you. It's called a double-napped cone. So, for example, this here in this shape, in this drawing, you'll see that's the upper nap, and of course below it is the lower nap of a double-napped cone. Now, if a flat surface crosses this double-napped cone at various angles relative to the generator, then the angle of the generator, what is the angle of the generator? It's going to be this angle, call it theta. So relative to the angle of the generator, the surface crosses, for instance, here, looks like it's crossing at an angle, and the surface is crossing the upper nap of the cone at an angle that is most likely greater than the angle of the generator, which is that theta that I have here. So when that is the case, of course, don't worry about the angles here. I'm just trying to state how these various shapes could occur relative to the generator. So if the surface crosses in such a way that it crosses the upper nap or the lower nap of the cone in such a manner that we can see here this surface, it's what's on the outside of the cone. Remember, the cone itself is hollow because of the rotation, so there's nothing inside the cone. It's a hollow cone. As a result, we're going to get any one of the 4 conic sections. So again, the reference to conic section is the intersection of a flat surface and a cone. The impression that it leaves on the outside of the cone is what we're interested in. So in the case of ellipse, you can see that this would be how the ellipse is formed. Now, if you trace the surface near the apex of the cone or the vertex of the cone, you can see that we get smaller and smaller ellipse, not circle, but ellipse. And there you go. We have ellipse, ellipse, ellipse that's getting smaller. So ultimately, that ellipse is going to degenerate to a single point. In fact, every one of these conic sections have a degenerate case. So remember, in the case of ellipse, the ellipse will degenerate to a single point. And we will see an example. In fact, I'll do an exercise where you will see how that happens. And then in this case, if the surface crosses the upper or lower nap, doesn't matter. It could be the lower nap of the cone, like that. If it crosses it in such a way that an impression, what's on the outside, forms a parabola, that's the case in here. The parabola actually, if you continue on the parabola along this line, the parabola actually degenerates to a line. Okay, to a line. And in this case, the ladder, we have the hyperbola. With hyperbola, again, we have this flat surface that is parallel to the generator. So if it crosses it, it will produce a hyperbola, which part of that hyperbola is outside one nap. The other portion is the upper nap of the cone. All right, so we have these three conic sections. A hyperbola, by the way, like it could be like this, the hyperbola. The hyperbola could generate to two crossing lines, as you can see here. There you go. That would be the degenerate case of a hyperbola. Two crossing lines. So parabola to a single line, hyperbola, two crossing lines, and ellipse degenerates to a point. And also there's a circle here. If the flat surface that crosses the upper or lower nap of the cone, it crosses it in such a way that is parallel to the base of the cone. Okay, the surface is parallel to the base of the cone, then the impression that's left on the outside of that nap of the cone will leave a circle. A circle, again, could be very tiny. Ultimately, the circle will degenerate to a single point. So ellipse and circle degenerate to a single point, parabola to a line, and hyperbola to two crossing lines. Now, what we're interested in this chapter, and all in all, is the equation of these conic sections. Okay, so we're going to look at the equation of a parabola, ellipse, and hyperbola. We've already talked about circles in great length before, so most likely we will not talk about circles, but that circle is a fourth conic section. All right, so now that we know about the conic section, let's actually look at the definition of a parabola. A parabola is the set of all points, or the locus of all points in the plane, that are equidistant. So there's the key word here. That are equidistant from a fixed point. The fixed point is called the focus, and a fixed line, and the fixed line is called the directrix of that parabola. Okay, and this is the figure that we're looking at. So if you look at, again, the fixed point that they're talking about here is this point. The directrix would be this line. Now, again, these are not part of the graph. These are more of a reference to significant portions of relative to the graph. What are relative to the graph? The graph itself is that. Okay. Now, if you notice here, based on the equidistant statement here that we have, these points, so distance from a fixed point focus to a point on the parabola is the same distance as the point to the directrix, and both of these are d. All right, so that would be, so this point P qualifies, in other words, this point qualifies as a point on a parabola. Now, for what I have here, if the focus here, directrix is here, for instance, this will not be a point on the graph of, let's say, this parabola. The reason, because look at the distance from focus to that point and that point to directrix. They don't look the same, right? So none of these points qualify. The only unique points that qualify are the ones that are looking at here, the graph of the parabola. Okay, so we'll look at the equation of this in just a moment, but keep in mind again, what's important is that this distance is equal to also this distance. We'll talk about these in a moment. Let me not get into that yet. Now, before I forget, I put the very interesting reflexive property of parabolas here for you. The reflexive property of parabola tells us, or is that any incoming rays, and these rays could come in at an angle, by the way, okay, at an angle here. So they don't have to be parallel. They show parallel just for simplicity. But it doesn't matter at which angle alpha it comes in. It will reflect to the focus. So that's very interesting. Again, I have an incoming ray, hits it here, it reflects to the focus. So all of these rays will collect at a point called the focal point or the focus. And you will see a good example of this one is a radio telescope that is the shape of a parabola. Now, an application that we will actually solve. By the time we get through this lecture, we will be able to solve this problem. So the problem, this is a radio telescope. It's a real life example, by the way. And again, I find it remarkable, something that Apollonius did over 2,000 years ago. We use it still. Very little things, not too many, I should say, ideas of mathematics have lasted as long as this one has, which is so widespread. They may exist in theory, but the applications even today exist. So that's very remarkable, the work that Apollonius has done for us. So this one actually very interesting. If you look at this parabolic radio telescope, this is a giant telescope. Look at the diameter of this telescope, 300 feet. 300 feet, that's exactly the size of a football field, right? The playing portion, excluding the end zones. If you add the end zones, then you add another 60 feet, right? 30 feet for each end zone, 10 yards. And so 300 feet across, that's exactly the size of a football field, which is massive. So we'll be able to write, based on the description that's given, we'll be able to write the equation, and the receiver is here. That's the focal point, by the way. So the incoming rays, they hit the surface of this, the parabolic surface. Remember, it's hollow on the inside. They hit the surface, and they reflect here. These will come in and reflect here. There you go. So no matter how the rays come in, they all will be reflected at that collector or the receiver. All right, so let's begin by looking at the equations. Usually I write the equations myself, but this one should actually do just as well. It just the graphs look much better, not done by hand, and they seem more accurate of what I want to point out. Now this form of an equation of a parabola, by the way, we call it the directrix form. So far we've seen parabolas before. We looked at the polynomial form, we looked at the HK form. This is the directrix form of a parabola. Okay, so for example, for vertical parabolas, let me put in my lines here. Okay, so for vertical parabolas in polynomial form, if you remember, those were y equal ax squared plus bx plus c, the quadratic function. And we had the hk form, which is y is equal to a x minus h squared plus k. All right, and we will see the parallel between the HK form and the directrix form. This is for the vertical parabolas, and for the horizontal parabolas, which is what this one is, so you simply switch the x and the y. So the polynomial form is x equal ay squared plus by plus c, right? And of course we have the corresponding hk form, which is ay minus k squared plus h. Here the vertex of the parabola we said was at hk. We never talked about the focus of a parabola. Vertex still at hk. All right. So what I want to point out on these equation is again the importance of this p, which is the distance from vertex to a focal point or focus, and the same distance if the parabola is vertical or horizontal, it will be the same distance to the directrix. Both of those in absolute value are p. Okay, if you look at this distance, that's p, so is this distance, again in absolute value, because one is above, one is below 0, so this sign, negative, positive, come into play in here. But if you look at the absolute value of them, they're the same distances. So that's important. And the other important fact I want to point out is that the focus of a parabola or any conic sections we look at, the focus will lie in front of the vertex, this being the vertex right here. So remember, focus in front of the vertex. So that will be a hint as to how we set up the equations later on. Focus in front of vertex, and directrix is behind the vertex. See the directrix, and that's again the vertex. Directrix behind, focus in front of the vertex. All right, and the equation, of course, there's x squared equals 4py, equal 4py. Before we looked at the equation, for instance, for the basic parabola, y equal ax squared, right, without any shift. Now we have x squared is equal to 4py. So if you solve for y here in the directrix form, divide both sides by 4p, so we get 1 over 4p is x squared, correct? Now look at this and look at this equation. From that, we see the relationship between a and p. So a is equal to 1 over 4p, and we can say p is equal to 1 over 4a. That's how p and a are related together. Okay, remember. So they're reciprocal of each other, except the reciprocal about 1/4 of each other. All right. Now, horizontal axis of symmetry. Remember, axis of symmetry here is vertical for both of these. Now we're going to look at the horizontal axis of symmetry. Now, right here, that would be the axis of symmetry. Both of them is horizontal. If P is positive, parabola opens to the right. If P is negative, it opens to the left. And we have both of those in here. Okay. Remember, P and A are related to each other up here. If P is positive, A is positive, and vice versa. And in the case of a vertical axis of symmetry, if P is positive, the parabola opens upward. P negative, the parabola opens downward. All right. And one last thing, and then we actually, I'll do some examples with you here. This is a more general directrix form. Now you see again the close parallel to the HK form. So for vertical axis of symmetry, again the form we had was y is equal to ax minus h squared plus k. That's what it was. True. Which we can actually play around a little bit with this, bring y and k together. Okay, let's go y, subtract k from both sides, ax minus h squared. All right, so it's kind of looking like that. And if I solve for x minus h squared, That's 1 over a, multiply both sides by 1 over a, and that's y minus k, right? And remember, a is 1 over 4p. So 1 over a, therefore, you take the reciprocal, becomes 4p. And check this out. See how the hk becomes 4p y minus k. And that's precisely what that is. See how that worked? Beautiful. So the hk form and the vertex form are really the same if you replace a with p here, okay, in the correct form of p, which is 1 over 4p. All right, so the vertex isn't going to change in both cases. Here we have hk, and again, these are the directrix forms because they look at p here. Okay, perfect. And the focus is the distance, absolute value of p from the vertex. Remember, focus is always in front or ahead of the vertex. So let's take a look at an example here. Let's see how we can put these equations to work for us. So in this example, let me make one up. Suppose I want to do x equal y minus 3 squared. Okay, we want to graph this parabola. Now, let's also do a domain and range of these, but I'll wait for domain and range until we graph them, okay? It'll be easier to do, actually. Now, if you look at this form, and the correct form would be this one, right? Compare it to that. Let me write that form is 4p x minus h equal y minus k squared. All right, we can go with that form. So clearly in this form, 4p, well, h is 0, right? Because there's nothing plus minus x. So h is 0 and k is 3. Therefore, the vertex of the parabola, which is at hk, is going to be at 0, 3. So we got the vertex down. Now, 4p here is equal to 1, correct? Because there's no number outside of x other than 1. Therefore, 4p is 1. Therefore, p is going to be how much? Is going to be 1/4. All right. And if you think in terms of polynomial form, we say a is 1. Remember, a is 1 over 4p, which is 1 over 4 times 1/4, so a is 1. Because p is positive, or a is positive, the parabola will open, in this case, to the right, correct? Because p is positive. So we have the vertex, we know it opens to the right. Let's actually graph this thing now. And the vertex is actually up high. The vertex is at 0, 3 here, correct? So go 1, 2, 3. That's where the vertex is. And the parabola opens to the right. So I know it's going to do something like this, correct? Open to the right. The axis of symmetry is going to be a horizontal line. Horizontal line equation is y equal 3 in this case. Now, because I'm so close to the x-axis, I want to graph this rather accurately. I'm going to have to find the x-intercept. So how do I find the x-intercept? That's when y is 0. So in the equation, x equal to y minus 3 squared. There, just put 0 for y, and we get 3 squared, or 9. So the x-intercept is going to be at 9, 0. The 9, 0 is going to be, let's say this one. How's that? There, I call this 9, 0. So my parabola, it's going to go like this. And then if I reflect it across here, on the other side, the other branch goes like so. And there we have the equation graphed out. That will be the graph of this equation. All right, and remember, the axis of symmetry is the dotted line here. So now I can see the domain and range easily, right? So what is the domain? All possible x values, because there is no graph on this side. So there's nothing to the left of 0. There are no x's to the left of 0. My domain has to start from 0 and goes all the way to infinity. Remember, for domain, we look at the x-axis. Domain means what all the possible x values that I can plug into the formula, and the equation will be able to handle it. So 0 to infinity. The range, however, for this one is going to be negative infinity to infinity. Those are possible y values. Why is it negative infinity? Well, it can go like this forever. It can go up and down and up motion forever. And there you have that one. Okay, so domain is this. And just to reiterate, range, we look at the y values. All right, and I think we've pretty much done everything about this one. The focus, by the way, remember, let's say find the focus too for all of these. Focus is going to be distance from vertex to focus, that's p, right? So I'm going to add that p, which is 1/4. It's going to be basically right here, right? It's only a quarter away from 0, right? P is 1/4 distance in front of the vertex. So the coordinates of the focus, therefore, is going to be 1/4, that's p, and it's at a height of 3, 1/4, 3. Those are the coordinates of this point. There you go, and there is your focus. All right, and I think that's all we wanted to do with this one. Cool. Let's take a look at another exercise. So in this next exercise, let's say I have x minus 2 is equal to negative 3 y minus 1 squared. Again, this would be in the form x minus h equal right up here, equal 4p. I have it's this one. X minus h squared equal 4p y minus k. Now, one thing, by the way, the horizontal parabolas are not functions. See, they failed the vertical line test many times over. So vertical parabolas are functions, whereas horizontal parabolas are not functions. They're simply a relation. That's what they are. They're simply a relation. They're not functions. So the things that require a function, the prerequisite are the things we do that require we have a function to do that, does not apply to the natural horizontal parabolas unless somehow we restrict them. Like, for example, look at the range from 3 to infinity only. Let's say just look at that part of it. Or let's look at something that's from negative infinity to 3. Let's look at the lower branch only. Together, we cannot look at both of them. That's if you want to force them to become a function, partially. All right, so this one, for this one, again, h, this is h, so vertex is going to be at h, and k is 1. And negative 3 for p equals negative 3, so p is going to be negative 3/4. Remember, p is a real number. Could be positive or negative. Negative means the parabola opens to the left in this case. And because the square is on y here, by the way, not on x, we know that these are horizontal parabolas. All right, what else do I need? I know the vertex. Let's actually draw this thing out now. Here's x and there's y. Okay. And the vertex is at 2, 1, 1, 2, 1, right in here. The parabola opens to the left again because I'm near the x-axis. I need to find the x-intercept. My x-intercept, that's when y is 0. X minus 2 equals negative 3, 0 minus 1 squared. X's add 2 to both sides. Negative 3, 0 minus 1 is negative 1 squared is 1. 2 minus 3, negative 1. Good thing. There we go. That's where it's going to cross at negative 1. That's where it's going to cross the x-axis. There you go. That's that part of it. And if I reflect this across to get another point, you see, by the way, how I'm getting, in order to graph any parabolas, by the way, you need 3 points. 3 points. 1 point has no choice. It has to be the vertex, because that's the turning point, right? Wouldn't do me any good if I say I have my 3 points here, right? Well, where is this going to turn? Is it going to turn here? Is it going to turn here? Here? Where is it going to turn? So the turning point you must have, that's the vertex. And the other 2 points, usually we get x, y intercept, the second one. And the third one we get by reflection across the axis of symmetry. All right, now the axis of symmetry of this one is going to be y equal 1, correct? That's the y value right in here, right? The k in the hk form. Perfect, so we graphed it. Now let's do the domain and range. See, when I graph it, then it's easier to see my domain and range. Otherwise, you have to do this in your head, try to argue or ration how it's going to go, or reason how this is going to be. Well, domain all possible x's. Well, x has to be less than 2 in this case. Notice there's no graph to the right of 2. So it's just going to go from negative infinity up to 2 including. And the range again, the range is possible y values here. And this would be the range. Negative infinity to infinity. That would be the range. Perfect. So we got the domain, we got the range, we got the x-intercept, and we're good. We're golden. And we got the axis of symmetry. Oh, the focus, of course. Now the focus again is going to be in front of the vertex, so that means it's going to have the same y value. The focus and vertex, these are collinear points. That means they lie on the same straight line. So I know the y is 1. Now we are at 2. P is negative 3, right? So from 2, I'm going to go 1 to negative 3 to the left. So that puts me at negative 1. That's actually where the focal point is. So it's going to be negative 1, 1. That's where the focus again is. That's F. Focus in front of the vertex. Oh, let's do directrix too, might as well, right? Because we talked about directrix, but we never worked with it. So where is the directrix in this one? Remember, directrix is also P distance behind the vertex. P is negative 3/4. Oh, I didn't do this right. No. Sorry, so sorry. It's not 3 units ahead. I don't know what I was thinking. Let's back up. P is how far focus is from the vertex. So absolute value of that is 3/4. So from 2 we actually go 3/4. So sorry, there you go. That's where, I'm sure most of you caught that. There you go. That's where the focal point is. So it's going to be 2 negative 3/4. That's going to be 1 1/4, right? 5/4. So P is the focus is going to be at 5/4 and 1. Again, not negative 3. I don't know what I was thinking of that one. All right. And there we have it. So we got the focus done correctly. Now let's do the directrix. So directrix would be equal distance, and actually that's what helped me catch my error. The directrix is also equal distance in absolute value, equal this time behind the vertex, right? So we're going to go 3/4 behind the vertex. That would be the directrix right in here. That's 2 add 3/4 to it. We get 2 3/4, which as an improper fraction is 11/4, right? So the equation of directrix is x equals 11/4. That's what that is, 2 3/4. Perfect. So we got all that we wanted about this one. We didn't do the y-intercept, by the way. We could, if you want to find the y-intercept, it will take longer. That's why I didn't do it. You have to set x equal to 0 and solve for y. Let me do that on this one. Y-intercept. For y-intercept, x is 0. Looking at the original equation, this one, negative 3y minus 1 squared. See, x-intercept is much easier for these than for this one in particular than y-intercept was. So now we're going to expand the binomial. Let's divide both sides by negative 3, by the way. So that's just 2/3, right? So we get 2/3 equals the square of the binomial y squared negative 2y plus 1. And subtract 2/3 from both sides. Well, 1 minus 2/3 is 1/3. You see that? Let's not worry about this one. If you have to graph this, let's say with a software that asks you to plot 3 points, do your vertex and do the x-intercept and do that one. That would be much easier than to do the y-intercept and let the software figure out the y-intercept. I'm just going to say solve by quadratic formula, because this is not factorable. Everything is factorable, but it's not factorable using rational numbers or integers. The quadratic equation, negative b plus or minus b squared minus 4ac divided by 2a. So that's going to be, and a is 1, the coefficient in front of y squared, a is 1. Okay. A is 1, and let's see, actually, yeah, in front of this quadratic equation, a is 1. So this would be 2 plus or minus 4 minus 4/3. Square root of that. 4 minus 4/3, that would be 2 and 2/3. Square root of that. 8/3. You see that? That's not going to be rational. So let's not waste time on it. All right. Let me just leave it for you in case you want to pursue this further yourself. I'm just going to let it go. All right. Let's take a look at another equation. So this one, another example. Suppose now I have the polynomial form. Okay, that's not the vertex form, but we do want to find, again, the things we found before, the vertex form and all of that good stuff. So in the polynomial form, to get it, by the way, to the directrix form, we have to complete the square. Okay, complete the square in y. So I'm going to go y squared plus 4y and push 2 out of the way. Now remember, to complete the square, the coefficient on y squared has to be 1. Keep that in mind, which it is 1. If not, we have to factor something. Oops, sorry. I'm not sure what happened here. Okay. And that coefficient is 1. So half of the coefficient on y is 4. 1/2 of 4. And then we got to square it, right? So I'm going to go half of 4 squared. That's what we're going to add. Half of 4 to 2 squared is 4. So that's going to be plus 4. And on the same side, I'm going to subtract 4. So I haven't changed the equation. See, 4 minus 4 is 0. And there we have it. Now, what's in parentheses is going to be a perfect square trinomial. Outside, we get negative 2. Move negative 2 to the other side. It becomes x plus 2 equals 1 times y plus 2 squared. And the reason I'm writing it like this is because we want to get it in the standard form, right? The standard form is this, right? X minus h squared, or this one right in here. It's y minus k. Squared is on the left side. The non-squared term would be on the right side. So y minus k squared. And there you go. Let me change the 1 here. Actually put 1 in front of that. And the reason, because that 4p is in front of x minus h. Let me back up again so you can see. You see this thing? The 4p is in front of the binomial that's not squared. Perfect. So from this, again, I can get the specifics. Now, remember the general form is in the hk form. It's x minus h. Well, I have plus 2. So for plus 2, I can write plus 2 as double negative, right? So h is actually negative 2. Okay. H and k here are opposite in sign of what it seems to be in parentheses. So if it's plus 2, the opposite of that is negative. H is negative 2, and by the same token, k is going to be negative 2. So we got that figured out. And what about 4p? 4p, that's the number in front of the coefficient on the binomial on x. That's 1. So p is going to be 1/4. Okay, and p is positive. So this parabola, which has a square on y, means it's horizontal. It's going to open to the right. All right, we got a lot of information here. We got the vertex, right? Vertex is at h, k, and it opens to the right. We should be able to do this one. Let me do that. And vertex is at negative 2. Let's call that negative 2 right here. And it opens to the right. So let me find the x-intercept again, so I can make it more accurately. I can graph it more accurately. The x-intercept, that's when y is 0, right? So I'm going to get x equals 0 squared plus 4 times 0 plus 2, which is 2. I'm looking at the original equation. So x is equal to, in this case, x would be equal to 2. X-intercept is at 2, 0. 2, 0 would be here. All right, and then we just make it happen. And that's that part. Here's the axis of symmetry. Remember 3 points. So find the vertex, find the x-intercept, and they're reflected across the axis of symmetry. You pick up the other branch of that parabola. And here's a vertex, negative 2, negative 2. The equation for the axis of symmetry is y equal negative 2. And there we have this one. Now, we know what P is, right? Let's find the focus. The focus, that's always in, focus is always in front of the vertex. So it's going to be P, which is 1/4. 1/4 ahead of or in front of the vertex. Well, vertex, if you look at the x component, is at negative 2, add a quarter to it, so you get negative 1 3/4, right? The focus is right in here. The narrower the parabola, by the way, the closer the focus is to the vertex. The wider the parabola, the further it is away from it. So for example, if I have, just like what you see here, if I have a parabola this narrow, that's going to be the focus. But if the parabola is really wide, then this is going to be the focus. That's what those, the radio telescopes that we saw, those have rather wide diameter. So the focus would be in front of it. Of course, the greater the surface, the better the reception, right? The greater the capacity to get far signals. Right, because there's more surface area. All right, and there we have it. I think that's all we want to do on this one, right? If you're interested again in the y-intercept of this, you could try set the equation equal to 0, solve for y using quadratic formula. Now the last things, domain and range of this one. Again, from the graph, domain is going to be from -2 to infinity, and the range is going to be right here, -infinity to infinity. All horizontal parabolas have the same range, by the way. They're all -infinity to infinity, but domain could change. All vertical parabolas have domain -infinity to infinity. All right, perfect. So we got this one down. Let's take a look at maybe another one. How about how about this one? Let's take a look at, for example, let's try y minus 3 squared equals 12x minus 1. Okay, remember the number in front of the non-squared binomial, that's 4p. So for this one, 4p is 12, therefore p is 3, which is positive. This one, the square is on y, correct? If the square is on y, then the parabola right here, square is on y. So this parabola is going to open to the sides. P is greater than 0, so it's going to open to the right. Okay, and so we know that much so far. What else do I need? I need a vertex. We're given the HK form, HK, so vertex is at 1, 3. That's good. And we should be able to, the axis of symmetry is going to be, because it's horizontal, it's going to be y equal 3. That is the axis. K in general, K, y equal K is the equation. And let's graph this one. XY. Vertex is at 1, 3. So it's right here. Let's call that 1, 3. There's the axis. It opens to the right, correct? So it's going to go, I don't know, something like this. And what is the x-intercept? That's easy to find when y is 0. So let's do our x-intercept. Y is 0. I get 0 minus 3 squared equal 12 times x minus 1. -3 squared is 9 equal 12x minus 12. I'm distributing the 12. Add 12 to both sides. I get 21. 12 equal x. So x would be 21 12th, right? If I did this right. 21 12. If we divide the 3's out, we get 7/4. Okay. That's 1 3/4. That's 7/4 there. So our x-intercept is going to be at 7/4, comma 0. And what else? Oh, directrix and focus. We didn't do directrix on the previous one, did we? Let's go back to this one because it's so easy to do. Remember, directrix is going to be a vertical line there behind the vertex. And this distance is going to be p. 1/4 behind -2. So the equation of the directrix, this equation is going to be x equal, well, -2, go 1/4 back to the left, it's -2 1/4, 9/4. That's the equation of directrix. All right, again, that's going to be a line here. Good. Let's go back here. Now we want to do the directrix. The directrix is going to be behind the vertex, a distance of 3 units behind it. So it's going to be 1, 2, 3. That's going to be the directrix. That line, vertical line, whose equation is going to be x equals -2. Because remember, we were at 1. Vertex is at on the x-axis at 1. We go back 3 units, puts us at -2. Now focus is in front of the vertex, equal distance 3 units forward. So we're going to go here now. True. The focus is going to be, we go 1 plus 3 makes it 4, and the same y, 4, 3. And There you have it. So for focus, I went to the right 3 units. For directrix, I went back from the vertex 3 units. Directrix is a line, focus is a point. And we have everything that we wanted to know, all that we wanted to know about this example. Okay. Now, let's try another example here. In this next example, suppose now we want to find, let's say in my example now, let's say we have, we want to find the equation of the parabola whose vertex is at 0, 0, and directrix is line y equal -1/4, a horizontal line, right? And let's say P, and well, we got to find P, but that should be good enough for us. Let's see, just based on that information, if we can write the equation of that parabola. So the geometry of this, based on just what I'm given here, vertex 0, 0, directrix is line y equal -1/4. That's a horizontal line, right? And call this, there you go, this is y equal -1/4. This is vertex. So that distance is going to be P, isn't it? And because it's -1/4 here, directrix, let's see, how is this going to work? Vertex is at 0, 0, correct? And directrix behind vertex. So this cannot be a horizontal. Agreed? Sorry, I'm not sure what happened there again. So this cannot be a horizontal parabola because directrix will be behind it. But the fact that directrix is below the vertex, that tells me this parabola has to open upwards, correct? Because it opens upward, its equation therefore is going to be what, y equal ax squared, right? Or we can write it as the following. The equation is x squared equal 4py. All right. And P is 1/4 here, right? So 4p, because it opens up, P positive. Okay, therefore we're just going to take that distance to be positive 1/4, or take absolute value of it. 4 times 1/4 is 1. Therefore the equation is x squared equal y. Y equal x squared, the basic parabola. Right? That was easy to do. The focus is in front of it, 1/4 above 0. So that's the equation. This one was easy. How about, let's do another one. Let's say I want to find the equation of a parabola. This time, let's say vertex is at 4, 3. Remember, that's your HK. And focus is going to be at 4, 5. Now let's draw what we have based on this information. Here's x, there's y. Focus is at 4, 5. Call that 4, 5. That's focus. Remember, focus is in front of the vertex. At this point, it could be up, down, right, left, right, anything. 4 choices. But the vertex should settle this for us. Remember, this is 4 and 5. Now, 4, 3. The vertex is at 4, 3. So that's going to be right in here. That's the vertex. Now this settles it. Remember, focus is in front of the vertex, so this parabola has to open up that way, doesn't it? Otherwise, any other way, focus will not be in front of the vertex. So we have a vertical parabola. So I'm going to go, the equation is x minus h squared for vertical parabolas, 4p y minus k. The square would be on x this time. We know the h is 4, and we know 4p, we'll handle that in a moment, and k is 3, so that's y minus 3, right? Now, the distance from vertex to focus, we are at 3, so p is 2, isn't it? P is 2, 2 times 4 is 8, and there is the equation of this parabola. So graphing it really helps quite a bit here. Okay, now we're done with this work. Let's go back and actually solve that the very first application problem that I posted. Let me bring the application and then we'll work it together. All right, so here it is. The problem again reads, the U.S. Naval Research Laboratory designed a giant radio telescope that had diameter 300 feet and a maximum depth of 44 feet. Remember, maximum depth, that would be this depth. It would be from the edge of the parabola to that point. That's the maximum depth of 44. In part A, write the equation of the parabola that models the cross-section of the dish if the vertex is placed at the origin and the parabola opens upward. So the geometry of this thing at the origin, so that's what they mean. The vertex is at the origin of the coordinate system. That's what they mean. And the parabola opens upward. You can clearly see here. Isn't that nice? There you have it. The parabola opens upward, and this would be the focus. True, where the receiver is, the collector. Now, for this one, because again, it's a very basic parabola, y equal ax squared would do, right? That's in the polynomial form, and if a is 1 over 4p, we can say x equals 4py. So both of these could model the parabola. Now, the thing that we need is this. We are given the diameter is 300, right? So I'm going the diameter. Let me draw this thing over here. So that would be our dish, right? And here's 0. This point is going to be what? Because it's 300 feet across. So from here to here is 300 feet, right? Across. So by symmetry, the coordinates of this point would be 150. The other would be negative 150. And we told the maximum depth is 44 feet. So that's the distance from the top to the vertex, top to the bottom. And there you go. That's what we have here. And this was again the depth of 44 feet. Now for this one, we can actually, all we need to do is determine A here, correct? Or 4py. So A is going to be, I'm just going to plug in these coordinates into the equation. So when y is 44, A times x is 150 squared. And from this, we're going to get A to be 11. It's going to be 44 divided by 150 squared is 22,500, right? Then we can divide, both of these are divisible by 4. You get 11 divided by 5625. So that's the coefficient. This will give us the full equation now. So the equation is y equals 11 over 5625 x squared. That's in polynomial form, right? Or if you go into x squared equals 4py, x squared equals 4py, you can also do that. Remember, a is 1 over 4p. So from this, we get p is 1 over 4a. Or, there we go, 4a, that would be 4 times 44 over 22,500, right? Which you invert and multiply, you get 22,500. 4 only multiplies by the numerator of this fraction, right? 176. And there you go. That's what that p is going to be. All right, but we can leave it in this form, or you can do it with p, however you want to do it. Or you can actually you can actually what you call it, yeah, that's fine. We can simplify this one again. P is going to be 50, divide the 4's out, you get 5625 divided by 44. Notice it's almost reciprocal of A, but 4 times smaller. All right, now let's actually, we have the equation, by the way, at this point. So we're done with part A. In part B, the receiver must be placed at the focus of the parabola. How far from the vertex to the nearest tenth of a foot should the receiver be? So we want to know where the focus is, right? All right, so out of this work, since we have the equation up here, if I multiply both sides here by the reciprocal, I get x squared is equal to 5625 11ths y. So this has to be P, doesn't it? Notice I'm getting that directly from A. We found P here. We found P there, but we also can do it this way. So what's in front of Y is 4P. Okay, so this acts as 4P. So from this we can find P, but then we found P here again. So there's no point doing it twice. And P turns out to be, if you approximate this on a calculator, I get 127.8 feet. 27.8 feet rounded to the nearest tenth of a foot. So that's the answer. The receiver must be placed at the focal point 120, almost 128 feet in front of the vertex. So that's where the receiver has to be. That's the answer to part B of this question. Okay, so we are done. All that you needed to know about the parabolas, and hopefully this should help you understand the parabolas a little better and be able to do the homework problems. Thank you for watching, everyone. We're done.